Hey everyone, it's Miss Hu, your physics teacher. In this video, we're going to go through the concept of force on a current carrying conductor. This topic is in both the SPM and IGCSE physics syllabus. There's of course a lot to know about this topic, so if you'd like to know more beyond this video, please feel free to do your own research or watch my other educational videos. What I'll be covering in this video is just a general overview and information that you would need to answer the questions in your examinations. So let's get started. Now, in case you're wondering, wow, what a mouthful, current carrying conductor. Whew. So this just means a wire that has current flowing through it. And we want to observe how force is created on that particular wire. So we have to, we can't just say wire because sometimes you will find that a force can also be generated on something that's not a wire, like if you have a metal piece, for example, some random metal foil. You can also find a force being induced on this conductor. That's why such a long name. For the purposes of this video, though, I'll focus on a conductor that's a wire. Okay, so first things first, before we get to how the force is created, let's recall what we can remember about how magnetic fields look like. So we have on the left side here, this represents a magnetic field that's around the wire. So what we're looking at here, 2D diagram. So this is the wire. So imagine like, okay, if you have a piece of cardboard, here's the wire, you're observing here, okay, here's the wire from your point of view. So current could either be flowing towards you, from your point of view towards you, or away from you. For the purposes of this video, let's just take one example in this case. So let's say current was flowing into the paper. So this is the symbol for current flowing into the paper. If you can't remember or you have not learned about this, please watch my video on magnetic effects around a single wire. So here, now let's say this is the conductor, current flowing in. This is the symbol for current flowing in. Now remember, use the right hand grip rule to determine the direction of the magnetic field. So as a recall, all right, current is flowing into the paper, right? So away from you, right? So it's in this way. And you find that the magnetic fields are going clockwise, correct? Have your right hand, best sign, point it here, follow it, thumb pointing here, and watch how your fingers on your fist look like, going clockwise, correct? So going clockwise, here we go. So we know there are magnetic fields formed around a wire that has current flowing through it. On the right hand side here, we have two permanent magnets that we place at a distance from each other. So we have the north pole of this magnet. Now, of course, there's no such thing as one magnet being north pole and one magnet being south pole. But usually we draw this in the diagrams just to show that, okay, if this is a permanent magnet with the north pole on this side, north pole here, south pole here, this is the south pole, north pole. But because we're focusing on what's between these two magnets, we'll just assume this is the north pole, the south pole. Okay, long story short, magnetic field formed between the two permanent magnets. Magnetic field will flow from north to south. So what I'm drawing here in green represents the magnetic fields that are formed between these two permanent magnets. Now, we're going to learn what's the effect when you place this wire into this permanent magnetic field. So again, let's say this is current flowing in. We already know. Okay, I'm going to draw two separate colors now to make it clear. I'm just going to draw one circle this time. Okay, so magnetic fields are going clockwise, but for the permanent magnets, which I'm going to draw in green, going from left to right. Whoops, that was not straight. So let's try that again. Now, you'll find these are two different sets of magnetic fields, but they're magnetic fields. And magnetic fields are kind of like force fields. They're going to interact with each other. You cannot have a situation where, ooh, look, they're going to crisscross. Okay, yeah, no, there's no crisscross. You have to understand magnetic field. What happens is they're going to merge and combine with each other, and they're going to form an overall shape. So how do they combine? So I'm just going to reset this a little bit. You can see on the top here, the magnetic fields are going in the same direction, whereas at the bottom here, they're going opposite directions. So if they're going the same direction, they're going to get stronger. If they're going opposite, they're going to cancel each other out, so they're going to kind of be weaker. You can also think of it this way. The magnetic fields are trying to go from north to south. So imagine, hey, what's this? This yellow field has come and disturbed the flow. So an easier way then is to go with the flow. So here is like, fight. So it's easier if the magnetic fields could, imagine like, oh, okay, too difficult. It's just going to go with the flow. So you'll find, for the most part, it's actually going to flow above like this. Okay? So here is the overall result. You'll find that there will be more magnetic fields formed above the wire than there are below. This causes this is now an unbalanced set of fields. Now this causes there's no balance in the force now. There is a disruption in the force. So anything that's not balanced will of course try to achieve stability. So okay, unbalanced, right? So hey, come and disturb, kacau as we call it in BM. Okay, come and disturb. So get out, go away. You think that has come and disturbed the piece. So because above there are more fields, that means the magnetic field here is stronger than the other. This will create a force. What am I doing? Let's pick the color. Okay, it's going to create a force that pushes the wire out of the way. And it's going to go from the stronger field to the weaker area. So this creates a force in this direction, in this case, downwards. So this is the force that's acting on the current carrying conductor that's placed in a magnetic field. And that's how this force is created. So this kind of field that creates this force is known as a catapult field because it creates a catapult effect, right? It slingshots the wire out from the magnetic field. So that's the force. Now, remember, of course, that when it comes to science, we want to find an easy way to be able to easily predict the directions over here. So how do we determine the direction? So John Ambrose Fleming has discovered that, what we can do is we can use our hands to use as a quick predictor. So this is where Fleming's left-hand rule has come about. Fleming's left-hand rule, named after John Ambrose Fleming, obviously uses your left hand. So please use your left hand and don't try to be too clever and use your right hand instead, okay? Your left hand. So how you create the shape with your hand, please raise your left hand and follow the shape. So what you want to do is you want to create a gun shape with your hand, with your thumb and your index finger, and have your middle finger stick out like a trigger finger. Let me just make this a little bit larger so that again you can see. Okay, so your left hand, left hand, mirror image, okay, left hand. This is your gun. Okay, 90 degrees, please. And then you stick out your middle finger so that it's also 90 degrees. So everything is 90 degrees. Okay, 90 degrees here. Oops, okay, how to show you? 90 degrees here, 90 degrees here. So everything is at right angles. Okay, so have your hand stick out all 90 degrees like this. So your thumb, index finger, and middle finger will all represent different things. So I'm just going to make it slightly smaller so that you can see. All right, so what do each of these represent? So your thumb represents the direction of the force that has been induced. Induced here means to be created, to be generated. Your index finger represents a magnetic field. So I'm just going to write here. Okay, I'll just write magnetic field. And your middle finger here represents the current. All right, so how to remember this? So there are many ways to remember this. I know there are different books, different websites, you may have different suggestions. Here's my suggestion. You don't like it, please use your own way of remembering what each of these represent, but here's mine. I like to say, feed my cat. Where's my cat? Okay, don't worry, that hand is the cat, okay? Feed my cat. Why? Because F, feed, force. M, my, and then C, cat, current. So, feed my cat. Feed F, force, my M, magnet, C, cat, current. So this is my suggestion on how to remember feed my cat. Okay, so now that we know how to feed the cat, how do we feed the cat in this situation? Let's go back here. Okay, so how do we position this? Okay, so remember, force, magnet, current. Now imagine that we had no idea where the direction of the force is, but we do know the magnetic field and the current. So starting with the magnet, so the magnetic field is going from left to right. So have your index finger point to the right. Okay, now the direction of the current. Current is the middle finger, right? And current is flowing into the screen, into the paper. So your middle finger needs to point into the screen. So you need to position your hand in such a way, let me make this larger so that you can see. Okay, you need to position your hand in such a way that the middle finger with the current follows the current direction and your index finger follows the magnetic field. And you'll find, ooh, the thumb points downwards. So the thumb represents force, and that's why you can see the force is going downwards. Make sure you're using your left hand for this. Your left hand should look like this, right? Index finger pointing to the right. The middle finger is moving towards the screen, away from you. Your thumb will be pointing down. And that's how you can get the direction of the force. So here's another diagram now. So that was in 2D. Now let's try in 3D. So this is going to be a little bit tricky because of the video. And I'm trying to match this so that you can see this in mirror image. But I'll do my best and I hope that you understand. So now, okay, we have magnets here, north and south. And of course, we know the magnetic fields are going from left to right. So I'm just going to draw one magnetic field like that to represent, this is where your index finger should be pointing. Now this wire, imagine this wire is part of a circuit. So let's say current is flowing, let's say this direction. Let me make this larger. Okay, cover first. So I've maximized my video here so that you can try to follow what my hand looks like. I need you to have your hand follow this hand, right? Okay, left hand, left hand. So we've got magnetic fields flowing from north to south. So north to south. Okay, the wire is this way, current's flowing this way. Imagine your eye line is here. You're looking in such a way that the current's flowing away from you. So it's got to come towards me. So have your middle finger point towards me. So I'm here. Follow my hand, please. Index finger is this way. Your middle finger is pointing towards me. You'll find that your thumb is pointing downwards, which means that the force is going downwards. Okay, let me show you. Okay, that's how your hand should look like. Okay, index finger, okay, and then middle finger following, and your thumb points downwards. That's how you use Fleming's left hand rule in this case. So the force produced, let's put it in yellow. Okay, so force produced will be downwards. Here's another example. So let's say we have now, in this case, current flowing from left to right. So sometimes you can come across questions like this where they, they'll place the magnets in different positions and a wire in different positions. So Again, use Fleming's left-hand rule and let's figure this out. So I'm just going to, let's make this a bit larger and put it at the side here. Okay, so with my hand. All right, so again, have your left hand follow this hand. Now you can see the magnetic field is pointing upwards. Now, south is outwards, right? So north to south. The current is flowing from left to right. So north to south, left to right. And this force is coming towards you, out of the screen, out of the paper. That means the force created here is moving towards you. So in 3D form, it would look like this, okay? Moving this way in 3D. That's how you can use the Fleming's left-hand rule to determine the force, whichever the rotation is. Remember, your hand can rotate, your finger shape never changes. So, an experiment, whoops, let me put my face here. Okay, an experiment to observe the effect of force on a current carrying conductor could be something like this. So we have the direct current power supply connected to some wires here. So these copper tracks are exposed so that current can flow through this short copper wire. So these are just two tracks that are open. This short copper wire is free to move on these copper tracks. So they have to be exposed so that current will be able to flow easily through these wire bits, these copper bits. The short copper wire is placed between two magnetron magnets, which are basically permanent magnets. So when you switch this on, what happens is this will create a force that will move the wire, depending of course on the direction of the current and the direction of the magnetic field's form. The wire could potentially move, away or inwards, depending on the whole thing. So how is this able to tell us what's the effect of the force? So number one, of course, we can determine the direction, whether it's going this way or this way. And if we want to determine the strength of the force, think about it. The stronger the force, the further away the short copper wire is going to roll. So the distance traveled by the wire in this case would represent the force that has been exerted. Greater force, greater distance traveled. And then in terms of the factors which affect the force, there's two factors you need to consider. One is the set of factors that affect the magnitude of the force, and another is the set of factors that affect the direction of the force. So in physics, it's really quite simple, because if you know what creates the force in the first place, you can definitely determine what are the factors that affect it. So it's really simple. You know that the presence of current flowing through the conductor and the presence of the magnetic field of the permanent magnets can create the force. So obviously, the factors that affect these two depend on this. So what affects the magnitude of the force? Obviously, the magnitude of the current, as well as the strength of the magnetic field. Obvious, right? If you're talking about magnitude. I'm trying to create a space here. That's not happening. There we go. And then in terms of the direction of the forces, obviously the direction of the current is a factor. And so is the direction of the magnetic field. So that's how you can remember the factors affecting the force. So if the magnitude, obviously the magnitude of the things that created the current magnetic field. If it's direction, then the direction of those respective quantities as well. And then when we want to look at how magnetic fields affect a charged particle, so a charged particle in this case, for example, if you shoot an electron between the magnetic field, or if you shoot an ion, could be a positively charged ion or a negatively charged ion or a neutral ion. Well, if it's neutral, there's no charge, so no effect. But if you're shooting a charged particle that has a positive charge or a negative charge, there will of course be an effect. Why? Because if you can recall what you've learned about current, current is quite simply the flow of electrons. But remember, current and electron flow directions are opposite to each other. So if current flows, let's say, this way, the electron flow is the opposite, this way. So if magnetic fields have an effect on current, obviously it also has an effect on the electron flow. So how to differentiate, or how do we determine the direction? It's not difficult. Here's how you remember it. If, let's say, we're talking about a positively charged particle, in this case, you treat the positively charged particle's direction how you would with current. Because why? Current flows from positive to negative. So when a positively charged particle is moving, think of it as if it's aiming towards a negatively charged field on the other side. There isn't, but imagine there is. So you can think of it, okay, positive to negative. So when we want to use Fleming's left-hand rule in this case, let me make my face a bit bigger again so that it's easier to follow my hand. Now remember, you can rotate the wrist, but the shape has to remain the same. So this time, the magnetic field is going north to south. Magnetic field needs to point downwards. So now, for the positively charged particle, think of it similar to current. Current flows from positive to negative. So if we're looking at your current finger, the current goes from positive to negative. We're following that direction, positive to negative. So you can see from here, the thumb is pointing this way. It's moving away from you, which means that the force created here is this way. So this is the force, which means that when the charged particle travels within a magnetic field, it's going to deflect. To deflect means to change direction. It's going to deflect and change direction and travel into the paper. Okay, it's going to travel away from you. Now, what if we have an electron, like a negatively charged particle instead? So, oops, now my face is blocking. Let me move this out of the way first. Okay, so now if, let's say, we have a negatively charged particle, like an electron. So if the electron is moving, it's opposite to the current direction. So it's as if it's moving from negative to positive. So how we use the hand in this case? Your current needs to be opposite to this direction. So again, north to south, so pointing down. But this time, instead of the current following the charged particle direction, remember it's from positive to negative. So because in terms of your middle finger, it's positive going to negative. Okay, it's from positive going to negative. So if it's now negative to positive, you need to rotate this so that this is now like this direction, negative to positive. Your middle finger needs to point this way, right? So north to south, now it's negative, positive. Your thumb is now flowing out of the paper. Okay, it's flowing out, which means that the force, whoopsie, is going in this direction. That means that the electron, okay, I can make this smaller now, the electron or the negatively charged particle is going to deflect and change direction so that it travels away and out of the paper, okay, towards you. So that's how the magnetic fields affect a charged particle that's traveling within a magnetic field. So it also creates a force that changes the direction of these particles. So I hope you have found this video educational and helpful and not too confusing. And I hope you know how to use Fleming's left-hand rule after watching this video. So if you found this video helpful, please click like and subscribe for more lessons, solutions, and exam strategies by your physics teacher, Ms. Ho. Happy studying!